So in this problem, we are required to find the vertical width of a binary tree, and the example is like this. Basically, if this is the tree given to us, so we are required to find the vertical width, which is basically number of lines we are able to form here. For example, this is our given route. So whenever I travel to the next left node, which is on the different level, different horizontal level. Okay, so just assume that I am giving it a number of 0, and whenever I will move to the left hand side, I would decrease that number or index. So initially it was 0, now it is minus 1, now it is minus 2, and we can see that there is no other node at this minus 1 level or this minus 2 level, but this node again becomes at the position of 0 because it was initially at minus 1 and we are moving on its right hand side, so we would increase the index and it would become 0 now. Okay, now all of these indexes are known to us, so now we would move to the right hand side, and it was initially 0 and this index now is 1 because we have traveled to the right hand side. Now if this index is 1 and we are moving to here, so this index again becomes 0. It means that although it looks like these three are not on the same level, but according to the horizontal distances theorem that we are trying to use here, all these three lies on the same line. That's why in the approach also, in the dry run also, it has given that there are six lines possible: one, two, three, on which these three nodes are there, four, five, and six. So this is the approach to find the horizontal distance, or the vertical vertical lines, or the vertical length. Okay, so the basic approach is that I would assign some indexes to all of these nodes. Okay, so the node is having basically the property of the right and the left node, but I would create a function which would also store the value of a particular index that I would assign. And I want to create an unordered set. Why? Because even if I would assign all the indexes to all these roots, but still there is no use because I don't know what is the answer. Because suppose that it would have an index of minus 2 and this would have an index of 3, but how to use it? Okay, so for that we would use a unordered hash set. Okay, and here we would store all the indexes, and we know that in the unordered set, basically no repetition is allowed. Okay, so you would be able to store only an index only one time. Okay, so just basically just assume that this index was 0, this is minus 1, this is minus 2. Okay, this is again 0, this is again 0, this is 1, this is 2, this is 3, and this is again 1. Okay, so now in the unordered hash set which I have created, I would store the indexes. So again, there would be, actually in the recursive code it would be slightly different. So basically we can just have a look on this code. This was the main function. Okay, and here first of all we have checked the condition that if the root itself was null, so we return 0 as the return type is given to us as int. And then I have initialized this variable hd, which measures the horizontal distance. And I have created this hash set h to store the indexes, and I have created my function help, which is having three variables, three parameters, basically root, the index, and the hash set. And at the end I would return the size of the hash set. Why am I saying this? Because suppose that I am able to store all the unique indexes in this hash set, so it would contain basically minus 2, minus 1, 0. Okay, uh, although there are three zeros, but again we know that it only stores the unique value. Okay, so it would be 1, 2, and 3. Now if I check what is the size of this hash set h, okay, so we can see that it has a size of 6, and which was our answer because all the roots were having some values of indexes, and they were passing through these lines. You can imagine these lines, that these lines are passing through all the nodes having the index as 0, at here as index 2. Okay, so this is the basic approach. And we can see that it works on recursion because we have recursively called this function. Also, whenever we travel to the left hand side, we decrease the index. So that's why when I am calling the left hand side, I am decreasing the index by 1. Then whenever I am increase basically checking the to the right hand side, I am increasing the node. I have put the base condition that whenever you find the root to be null, we return, because this is a void type function, because we are using it here in our main function. And also, if the suppose that for this node, if I have got its left hand side value and right hand side value, so I basically simply add this term into the hash set. So we can see that the time complexity is O of n here, because we are at least visiting every node once. Okay, and the space complexity is somewhat like we are doing computations on it. For the stack space is used for the recursion, that is one thing, and we are using also the hash set. So it is approximately about O of n. So the space complexity and time complexity for this code is O of n.